Hi everyone, I'm Bhuvan Belur. I'm the president of Space Enterprise at Berkeley, UC Berkeley's liquid-fueled rocketry team. Recently, this past weekend, we completed a successful Hotfire of our latest vertical demonstrator. But what is a Hotfire? So if you look at a group like SpaceX and their latest Starship launch, there's a lot of testing that goes into making sure that a Starship is ready to launch before you can launch it, namely engine tests or Hotfires. Starship will go ahead and do a static fire where they fire the engines at full thrust while holding the whole system down to make sure that all the engines are operating nominally and that the system is good to go before launching it. Because if it's going to blow up, you want to find it on the ground instead of in the air.
Before we continue, we'd like to thank our sponsor, U-Haul. As a college team, it's pretty difficult to transport a rocket over 300 miles across California, and U-Haul trucks are a real lifesaver there. We would not be able to do our testing without them, so thank you again to U-Haul, and let's get back to learning about Hotfires.
Hey, I'm Jade. I'm on the simulations team here, which is kind of more the behind the scenes stuff. So I'm really excited to speak to Bhuvan and see what happened last weekend. So obviously there's so many important things that you need to measure with a Hotfire. Can you tell us about some of the most important things you found?
Yeah. So when we're collecting data, we're looking at a bunch of different things. So we're looking at thrust to see how much thrust the engine is producing. That's obviously really important because when we launch, we want to make sure that we're going to go as high as we want to go and that the engine is producing what it's supposed to do. So thrust is a big one. But what's also really big is pressures. We're really concerned about pressures in our tanks, pressures in our injector that feed the rocket engine, and pressures in our chamber, in the chamber of the thrust chamber. That's super important because that kind of directly correlates with thrust and allows us to calculate metrics like efficiency, C-star, that kind of thing. So those are really big. And another one we're looking at is temperatures. We obviously want to make sure that the engine isn't overheating and melting, which is a lot of why we do these tests on the ground. And so we're looking at temperatures all across the engine to make sure it's not melting through as it's going through this combustion.
Right. Okay. And something that's pretty cool about the engine and the rockets that we design is that they're liquid bipropellant. Which may be kind of unfamiliar. Would you mind talking about what
so
that means?
A liquid bipropellant rocket engine, it just means that bipropellant is using two propellants, a fuel and an oxidizer, and liquid just means that the fuels are both liquids, and that's in contrast to solid-fueled rocket boosters, where both fuel and oxidizer can be solid, mixed together in kind of like a brick of explosive. There are also hybrid rockets where one of the two, usually the fuel, is the solid, and then you run a liquid oxidizer over it. But with liquid bipropellants, you have both of your fuels as liquids, and you're forcing them through into the chamber of the rocket engine, mixing them, atomizing them, and igniting them before igniting.
Right. Okay. And obviously, you mentioned temperature is really important. It prevents overheating, and when you're working with a rocket, that needs to be managed. So obviously, there's cooling systems in the rockets. When would you say the temperature is measured during a hot fire? Are there certain points?
So we're actually collecting data through the entire process of a hot fire. So even before the hot fire, so right from when we start getting the system ready to load propellants on board, we're collecting data the entire time. And a lot of that data is really high frequency, so when we finish the day, we have gigabytes of data to look through. But it's super helpful to just have everything, because if anything goes wrong at any point, you want to know exactly why. So if your tank were to blow up while you're loading propellant, you might not think that you want to have tons of data at a boring point where you're just loading propellant, but if something goes wrong, the data becomes really important.
Right, okay. And how long does the engine actually burn for in a typical hot fire process?
So it varies, and usually we'll scale up as we gain confidence with the engine. And so we'll usually start with really short duration burns, like 2-3 seconds. And a lot of that is just to test ignition and make sure there's nothing drastically wrong with the system. And once we're happy that the engine is working well, then we'll scale up. And so that can go all the way up to as long as 18 seconds is the longest we've done before. With our new engines, we're looking to go even further to more like 26 seconds.
Great, okay. And obviously we have some data, and we're going to show some of that soon, but in a snapshot, how do you feel that Hotfire test went last week?
So I'd say it's definitely a mixed bag. There were some good parts, there were some bad parts. One really great thing is this was our lightest vertical system yet. And so mass is super important for rockets. You want to be as light as possible without fuel, and then be able to take on as much fuel as possible. And this system was able to house a little more than double the fuel of our previous rocket systems, while being less than a third of the weight. So significant dry mass reduction, which is really important for us. That involved designing custom tanks that have really low factor of safety, which means they're super close to breaking. And while that sounds like a bad thing, it's actually a really good thing, because if they're not really close to breaking, you're carrying a lot of extra mass. And so these were low factor of safety tanks that we had created ourselves and then hydro tested to make sure they could take the pressure. And they saw through Hotfire successfully. So that was really awesome. And there were some feed system changes as well, which we were really happy with. So we have an autogenously pressurization. Let me say that again.
Yeah.
We have an autogenously pressurized system where we use our oxidizer, nitrous oxide's pressure, to force both of our propellants through to the engine. And we make use of a piston in one of our tanks that transfers pressure between one propellant to the other. And that's a really scary thing because you have this seal that is an interpropellant seal.
Right.
That's one of the only things stopping your fuel and your oxidizer from mixing. And if they mix before they're meant to, you have a really explosive mixture ready to ignite with any kind of activation energy. So I'm really glad that didn't happen and that all of our testing kind of worked out. And so I was really pleased by the feed system performance, but there was some downsides. So we did have a hard start. A hard start is basically where you accumulate some extra propellant before ignition in the chamber, and that leads to a quick ignition and an overpressure event. So you suddenly ignite all of this propellant, and you have a high pressure in the chamber, which it wasn't designed for before the thrust chamber behaves normally. And in this case, it was a pretty bad hard start. And so if you look in the data, you can see a few seconds after we start letting propellant flow to the engine, there's massive pressure spikes. All of our load cells actually broke from shock, which tells us that the initial thrust event was over 3,000 kilograms of thrust, which is quite a lot. So that was bad, but the system, it was still there. The damage actually did not look too bad. When looking back at the system, it's very recoverable, but the burn wasn't nominal because of that.
Okay, got it. And so I remember my first work session with Seb, you and I spoke about nitrous oxide and how you switched to it a couple of years ago. And can you speak a little bit more about what made the switch and why it works more efficiently for the engine? Yeah,
so that's a great question. We were inspired a lot by a group called Half-Cat Rocketry, who are doing some amazing work. But our previous systems they're all pressure fed, but our previous systems had a separate pressurant tank, a kind of COPV, a scuba tank that held really high pressure nitrogen gas that we would use to pressurize our fuels and force our fuels down into the engine. And that is really heavy. It's heavy and it's complex because you now need to carry a really strong tank that can take super high pressure in order to be able to maintain pressures in your propellant tanks. It means you now have to have regulators that regulate that pressure down for your propellant tanks. And it's a lot more complex of a system, right? If that regulator fails, now you can have really high pressure gas in your lower pressure propellant tanks. So we've launched 2 rockets that way, Eureka 1 and Eureka 2, and we learned a lot that way. But we think we can get to a much lower mass, more efficient rocket by using nitrous oxide, because nitrous oxide at room temperature has a really high vapor pressure, which means it's self-pressurizing. It essentially will feed itself out. Which is really nice because it means you don't have to carry this extra pressure. And by using this piston system where we share the pressure for both our fuel and our oxidizer, we can cut out a lot of mass on the rocket, which we think will get us to space.
Yeah, really interesting. So obviously you guys travel all the way down to the desert, do a nice road trip.
Yes.
And I heard the weather was quite cold. I wanted to ask, are there any sort of precautions you have to take when the weather's that cold and you're hot firing a rocket? What kind of stuff do you have to look for?
Yeah, absolutely. So just from a personnel perspective, it's kind of chilly out there. A lot of us just sleep straight out in the desert, which means you've got to bundle up, bring a warm sleeping jacket, because if you don't, you will freeze. And I've made that mistake before. From an operations perspective, it doesn't change too much for us. One thing that it does change is the pressure of the nitrous oxide changes based on what temperature it's at. And so if our source bottles are at a lower temperature because it's cold outside, they'll be at a lower pressure. And so that can affect our fill procedures. It can mean that we have to be more wary of the pressure dropping in those bottles as we fill our rocket. But even though it was cold, it was still fine for us. We didn't have any issues.
Great, awesome. Okay, so let's look at some of the data that we have.
Yes.
Okay, so can you tell us a bit more about the tank injector pressures, this graph that we're looking at?
Yeah, so right here we're looking at most of the pressures on our system, and as I said, pressure is one of the most important things when monitoring on our system. And so on this graph we can see the pressures in our nitrous tank and our isopropyl alcohol tank, or our IPA tank. And both of those are about the same pressure because they're sharing this pressure via the piston I'd mentioned before. And we're also looking at the injector pressures. So the IPA and nitrous injector PTs, or pressure transducers, are located right at the kind of inlet of the engine, and that's right where propellant starts to enter the engine. And so you can see that there is zero pressure there right until we start the burn, and that's when we open our main valves and we allow propellant to flow into the injector and then into the chamber. And so we can see this rise in both of these two at the exact same time, which is nominal. That's what we wanted. But you'll note we don't see ignition until about 200 milliseconds later, and this is where things start to go wrong. If you zoom in on this area, you can see everything kind of goes a little crazy at this point. There's a little blip in chamber pressure, but not a crazy high spike. There is a big spike in nitrous injector pressure. Our APA injector pressure also starts to go up a little bit. The tanks see some pressure change here. Everything kind of goes a little crazy at this point. And the reason for this is because we had a hard start. And the reason that happened is we have an out-the-throat igniter. So the igniter is the part of the system that ignites the rocket propellants. And ideally, you want to ignite inside the chamber as soon as the propellants start coming in, and you'll have a clean burn. But what happened in this case is that igniter blew out, and you can see that in the footage. It blows out, and propellant starts to keep coming out. It pools a little bit outside, and then ignites outside of the chamber, flashing back into the chamber, causing this big explosion outside and hard starting the engine. And it's when all these pressures go crazy, that's when the hard start happens.
Great. Okay, so in a perfect world, if this Hotfire went according to plan, what would this sort of graph look like?
Yeah, so ideally, you wouldn't see all this spiking all over the place. Our chamber pressure would not sit so low for the duration of the burn. It would rise up to nominal, which is more like 300, 400 psi. Our tank pressures wouldn't have this kind of shake in them at that point. But most importantly, the injector pressures would look nice and smooth and fall and decay, just as they continue to do for the rest of the burn. But it's mostly that chamber pressure. And the reason our chamber pressure ended up being so low is because this hard start blew out our nozzle. And the nozzle is super important for thrust, but it also means that our flow rates are way off. And so nominally, we'd see normal chamber pressure and our injector pressures would continue. Yeah.
Great. Okay, so in terms of mitigating that, what kind of stuff, I'm sure there's so much that goes into it, but what kind of things are you focusing on, or are we focusing on now?
Yeah, so there are a few different paths we can go. The most important thing we have to do is we have to get back to a point where we have really reliable ignition. And so we can either kind of refine this type of igniter, this out-the-throat igniter, or we can pursue a different option. And so we think we know how to make this igniter more reliable. We just need to provide more force that retains the igniter before ignition. And that's super easy for us to do. But there are other alternative igniters that don't have the same problem. So we're also exploring a cartridge igniter, which is where the igniter is a solid rocket motor that directs hot gas straight into the chamber from inside. And this is super helpful because it can't blow out.
Okay.
And so you won't have the same issue. Either you light or you don't light, assuming your timing is okay. And so we're kind of looking into that as well.
So we're going to take a look at the next graph, which is the engine load cells. Can you tell me a little bit about what's happening here?
Yeah, so we have 3 load cells on the system, and those 3 load cells are kind of spaced out evenly so we can detect any thrust asymmetry. They all detect thrust coming from the chamber into those load cells. And so what you would expect to see is at ignition, you'd expect to see a nice quick ramp up to our expected thrust. You'd see that to kind of hold and decay a little bit over time as pressures kind of decay, and then come down at the end of the burn. But what we see here is exactly not that at all. We see all of the load cells rail and just shoot straight up to 1,000 kilograms right at ignition and stay flat there for the duration of the burn. And those load cells we've now inspected afterwards and they're dead. And so our current theory is that the instantaneous thrust that the hot start produced shocked the load cells and broke the sensing element inside them, which means that our thrust data from this is unfortunately not very useful.
Okay, so for my own curiosity, I know you've been to many Hotfires.
Yeah.
Do you have a favorite one? And if so, why?
Yeah, it's a tough one. They're all special in their own ways. I'd say some of my earlier Hotfires were maybe even more special because I didn't know what to expect yet. Most special was our first launch of Eureka 1. That was our team's first launch of a liquid bipropellant rocket, and so that was really big for us. And it was just so crazy to see all this work that we put in, all these static fires where we'd fired the engine on the ground to see that thing just actually take off and leave the launch rail was super, super cool. Then another really good one was our heavy bulb Hotfire last semester. This was big for our team because we were really stepping up in thrust. Until this point, we'd only hotfired our first engine light bulb, which produces around 600 pounds of thrust. But we were stepping all the way up to an engine producing about 2,500 pounds of thrust. So all the flow rates were higher, the pressures were higher, everything was new and kind of big. And so that was really awesome to see kind of our team scaling up and creating and successfully firing an engine that was that much bigger than we had before.
That's awesome.
Yeah.
So this is obviously my first year at SEB, and I'm just understanding the adjustment just being on the simulations team, but you're president of everything. Can you tell us what that adjustment has been like? And I mean, if I'm not mistaken, this is your first Hotfire as president.
Yeah.
So how can you just tell me what this experience has been like?
Yeah. There's a lot that goes into a Hotfire that not everyone sees. A lot of logistics and a lot of even testing before the test. And when you take 50 people down to the Mojave Desert where there are scorpions and there's sun, and if they don't bring camping gear, they could freeze, and if they bring food, they're going to get hungry, and if they don't have water, there's going to be a problem as well. Even just past the actual testing, there's all these other things you have to think about, and then you have to think about the testing as well. Did our nitrous oxide arrive? Because if it didn't, we're screwed. Do we have our fuel as well? How is our system going to survive on its way there? Because there's some bumpy roads. There are lots of little small things that you have to think about, and if you get them wrong, you can end up wasting a lot of time in the desert. And so that's something we're always looking to improve on, is kind of our operations once we get there, because we have a set amount of time to do our testing, and we want to get as much done as possible with that.
Right. So how many days do you actually spend camping in the desert?
Yeah, so we drive down Friday morning. We leave at about 9 a.m. from Berkeley, and it's about a 6-7 hour drive. Yeah. So we're driving most of the day, and then we get to Far at around 5 or 6 p.m. When they let us in, and so we spend that night kind of getting the system ready, doing some leak checks to make sure nothing is loosened up, making sure everything is ready for the morning, and putting the system on that vertical I-beam that you see in the videos. And then we sleep overnight, not that long, and then Saturday morning we're up bright and early at 6 a.m., ready to go and get our tests done. And so Saturday morning we're just doing any final checks before we start running our procedures.
Right, okay. And obviously from the videos, it's easy to just see the hot fires and the flames, and it's so cool. But how many hours of work would you say actually goes into preparing it?
Yeah.
Once you're in the desert and setting up the vertical demonstrator and all those things.
Yeah, so the Hotfire is really just the end of the testing campaign. But to get there, we do acceptance testing back in Berkeley, which involves running cold flows with carbon dioxide and water. And the cold flow campaign can be, and often is, weeks longer, because the Hotfire is just a few days, but the cold flow campaign before that is a series of development flows to get us to the point where we're happy to Hotfire the engine. And so, honestly, that work takes a lot more time. It's weeks and weeks and weeks where we're there every day just getting this thing ready.
Right. And obviously we've been a part of that, having to make sure that these cold fires have been cold flows have been successful. Can you just explain in a little bit more detail what the data that you need from a cold flow and how that can impact our ability to perform a hot fire?
Yeah, so the big thing we're looking to make sure we can do before we go down to the desert is, can we feed the engine with the right flow rates of propellant it needs to combust and have nominal thrust? Yeah. And so that's all we're trying to kind of make sure we can do before we go. And so to do that, we have to make sure that we have to calculate the pressure drop across our system. So this fluid has to flow through plumbing at high flow rates, and it drops in pressure as it does that, and we want to know that pressure drop. We also have to calculate CDs for our injectors, so that's super important as well, and so we have to do flow testing to figure that out as well. But at the end of the day, we do all this flow testing so that we know what pressures to set in our tanks in order to have the right flow rates through the system. And so in that sense, it's very simple, but we just have to do some experimentation to get that.
Yeah. And this is an off-topic question, but when you're in the desert, do you pack food? How do you feed 50 people?
Yeah, that's a great question. So we are in the middle of the desert, and there is some power, but not a lot, and you won't have it through the night. Right. So yes, how do you feed 50 people? So we sometimes will grill, and so we on Friday night we got a lot of meat and some Impossible burgers and stuff, and put it all in a cooler, and we grilled that night, which was really fun. And then through the rest of the next day, we're lucky enough to have a lot of said parents who come out to visit us while we're there, and they always bring food, which is really nice of them. So that's always fun and really nice. But aside from that, it's a lot of like cup noodles, Pop-Tarts, whatever you can get to get through the weekend.
Okay, well, this is great. Like, everything from this Hotfire, I mean, you guys are just one step closer to what this club's mission has been from the beginning. I'd love to hear from your perspective what that kind of means to you. Yeah,
so SEB's mission has always been to send a liquid-fueled bipropellant past the common line, 100 kilometers to space. And so no team has done that yet. And so we want to do that. And this has been a big milestone. So we have we're really just getting started with our Eureka 3 development, and Eureka 3 is set to be our Spaceshot. And so it's first of all just awesome to be working on the rocket that we think will get us to space. And we've done some engine testing last semester, which was really cool, but it's been awesome to see this vertical system take shape, because the vertical system is in the end what becomes the rocket. And we broke a lot of boundaries with this. It was our first set of custom tanks that we were hot firing with, and that too with such low factor of safety. it was super cool to see a flight-like feed system that we know is super light work well in the desert, because at the end of the day, if the rocket's not light, it's not going to fly. And it's really cool to see this coming together and looking like a real rocket.
Yeah, thank you so much for coming on. We really appreciate it.
Yeah, thanks for having me. Yeah.